Hi everyone, welcome to our channel. I'm Niu Yanlong, a PhD student at the National University of Singapore. Today we will talk about measuring the small string stiffness in the lab using distributed acoustic sensing. Countries with limited land availability, like Singapore, frequently turn to land reclamation projects to increase usable space. This process typically employs cement stabilization technology. However, identifying the optical mixing ratio can be a complex task because of the difference in the soil composition. As a result, trial and error adjustments are often necessary to discover the most effective combination. So, optimizing the mixing ratio requires preparing and testing multiple samples, which can be both time-consuming and costly. Small string stiffness is a critical factor for cement-treated clay as it's directly related to the material's mechanical properties. Since a large number of samples need to be tested, equipment that can measure multi-samples with distributed and synchronized capabilities is very important. Over the last 2 decades, distributed acoustic sensing DAS technology has become increasingly versatile and has been utilized for subsoil survey and long-term underground monitoring. Despite its potential, there is a significant lack of research on the use of DAS for large-scale geotechnical testing. The working principle of DAS is based on the elastic radio wave scattering of laser pulse in the optical time domain reflectometry. The laser phase is linearly proportional to the vibration, and the single component string rate is averaged over the gate length. Standard optical fiber acts as a sensor array, allowing for the measurement of small string rates at a sampling rate up to hundreds of kHz. Additionally, the fiber is durable, and each channel is relatively inexpensive. DAS has several advantages, including high sensitivity for small string vibration, low cost per channel, and consistent measurement that overcomes the difference for individual receivers. DAS optical fiber is also easy to implement and has strong environmental adaptability. Our test setup modified the conventional free-field resonant column test configuration by incorporating the DAS. We also compare the dominant frequency measured by DAS with the accelerometer to verify its reliability. The accelerometer is attached on the samples. One is vertical to the axis and one is on the curved surface. The sensor and sample is coupled with hot melt glue. DAS optical fiber was wrapped around the sample circumference, perpendicular to the axis, that close to the edge. Our baseband test used a 4-meter gauge length and a channel spacing, with a 40 kHz sampling frequency. To demonstrate the robustness of our method with different materials, we use sample made of nylon, acrylic, cement mortar, and cement clay. To generate the active source, we use a small hammer that induces a measurable mechanic vibration without causing any plastic damage to the specimen. We perform strikes in both longitudinal and transversal directions to exact the material resonance. To generate the pseudo-passive source, we use the ambient noise in the lab, including the cooling fans in a DAS interrogator, over mixer vibration and manual taping during the sample preparation. For the active source, the collected time series signal is processed after each hammer strike by setting a threshold value to pick out the individual events from the continuous data. A turnkey window is applied to the data segment to reduce the energy leakage, followed by a high-pass filter to reduce the low-frequency noise. The cutoff frequency is determined based on the estimated minimum wave velocity of the measured sample. The individual time series signals are then converted into the frequency domain using the fast Fourier transform algorithm and stacked to obtain the final amplitude spectrum. Upon extending the amplitude spectrum before and after implementing our data processing method, we identify a significant decrease in the low-frequency component. This observation suggests that the main origin of the low-frequency signal is likely due to the external influence, such as the equipment or the operator-related disturbance, rather than being inherent to the test sample. Under the passive source, both receivers show low signal-to-noise ratio. The resonance peak is not evident in the DAS data even if we apply the filter. Since the resolution of the passive source is expected to be lower than the active one, we set a window length of 1,500 points and a sliding length of 300 points to size the continuous passive data. The same high-pass filter is applied to the signal to reduce the low-frequency noise. Additionally, calculating the autocorrelation function of the passive data at the time lag tau is also required to enhance the amplitude of the resonance peak for a given signal. The resonance peak induced by the passive source become detectable after implementing our method. Proceeding now to the results section, we will discuss our findings. Under longitudinal impulse, both the longitudinal and the transversal accelerometers detect a small peak at 5,900 Hz corresponding to the energy from the transversal mode. The longitudinal accelerometer identifies the dominant frequency at 9,700 Hz, which corresponds to the simple PV velocity, and the second higher longitudinal mode at 18 kHz is also observed. Thus, successfully detect two peaks correspond to the transversal and longitudinal mode that match well with the accelerometer measurement. Under transversal excitation, DAS and accelerometers both detect the fundamental resonance frequency at 5,900 Hz, but the second transversal mode at 11 kHz is only recorded by the accelerometer, possibly due to the low sensitivity of DAS at high frequency. The longitudinal accelerometer detects both modes, but with a higher amplitude for the longitudinal direction. In summary, fundamental longitudinal and transversal resonance measured by DAS and accelerometers and an active source are cross-validated. To identify a passive monitoring source, we also investigate the ambient vibration from various laboratory activities, including the cooling fans, the mixer vibration, and the tamping procedure. The longitudinal accelerometer detects the identifiable resonance peak corresponding to the transversal, longitudinal, and the first-order transversal resonance at 5,800 Hz, 9,600 Hz, and 11 kHz. The transversal accelerometer only detects the transversal resonance, while the longitudinal resonance measures both, indicating that the passive source contains more intense transversal energy. The cooling fans show some divergence due to insufficient energy and low sensitivity of DAS. DAS only detects the transversal resonance frequency for all types of passive source due to its multi-directional measurement property. The resonance peak becomes more distinguishable as the energy of the passive sources increased from the cooling fans to the mixer vibration and the tamping procedure. Overall, the impulse load-like source elect activities such as the manual-induced table vibration or the weight drop serve as the good triggers for the resonance accumulation. We also test the various uniform materials following the same procedure discussed above to test the robustness of our measurements. Dot and star symbols represent the measured longitudinal and transversal resonance respectively, as corresponding to the P and S wave velocity. The red color represents the active source measurement, and the blue color represents the measurement and the passive sources. Most results are located on the line of equality, indicating highly repeatable DAS measurements for various types of specimens in the high-frequency range of kilohertz compared to the accelerometer. FFR test is an impact resonance method that straightforwardly evaluates the simple dominant frequency and derives its corresponding small string stiffness. In this equation, M and G represent the constrained Escher modules respectively. Specimen's density is ρ, L is the cylinder sample length. FLN and lambda Ln represents the frequency of the nth longitudinal wave mode and corresponding wavelengths. FTN and lambda Ln represent the resonance frequency of nth transversal wave mode and corresponding wavelengths. As we can see, the measured stiffness closely aligns with the ground truth value. In conclusion, DAS effectively determines material stiffness with wrapped fiber optical cable configuration. Resonant frequencies are consistent for active and passive sources regardless of the excitation direction. Tamping procedure provides a stable resonant frequency observations. The benchmark study validates DAS accuracy and reliability, while DAS improves the efficiency by minimizing the repositioning. It exhibited a lower signal-to-noise ratio for the higher resonance mode detection. Thank you for watching. This video is sponsored by NUS Delta's collaboration. If you like it, give us a thumbs up and hit that subscribe button for more awesome content like this. Don't forget to click the notification bell to keep up with our latest uploads. Got any comments or questions? Feel free to drop them in the comment section below. We'd love to hear your thoughts.